Vector search often misses the bridge between facts. Entity linking plus Neo4j turns retrieval into graph expansion before the RAG rerank. You'll see how to connect the pieces into a workflow that links named things to connected evidence and orders the best context. I'm Professor Pi, teaching search and IR with simple Python. Entity linking for graph RAG fixes a specific blind spot. Vector search finds similar language, but it doesn't know which named thing a passage actually refers to. That makes multi-step relationships hard to surface. If we map mentions to stable graph nodes, we can walk connections and pull in related evidence that pure vector retrieval would skip. In short, the graph lets you turn local matches into meaningful context and reduces hallucination risk when the graph has curated facts. Here's the simple plan. Detect names in the query and map those mentions to stable IDs the graph understands. Walk the graph from those seeds to collect connected chunks. Re-rank the collected chunks for the question and send the best context to the generator. The fragile spots are linker accuracy and how far you expand. But the benefit is clear. Graph traversal surfaces indirect but relevant context. We will build a tiny live pipeline that proves the idea end to end. You will see a real Neo4j handshake, a simple spaCy entity linker mapping mentions to IDs, a toy graph ingestion of chunks, a graph expansion retrieval that follows relationships, and a basic reranker that prefers chunks mentioning the query concept. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we check we can reach the graph and avoid wasting time on later steps if Neo4j is unreachable. This snippet opens the smallest reliable path into Neo4j before we add retrieval logic. A graph retrieval pipeline is only useful if the application can prove the database connection works before serving requests. Graph Database Driver creates the official Neo4j driver. Driver.verify connectivity checks the server handshake, and driver.execute query runs a tiny read query. The credentials come from environment variables, so the code avoids hard-coding local secrets. The visible output shows Neo4j responded, which gives the rest of the tutorial a live graph connection to build on. With a live graph, the next need is stable IDs for mentions, so the graph can join on entities instead of raw text. This example turns surface mentions into stable IDs that a graph can actually join on. Text alone is brittle. Neo4j, graph database, and a product alias may need to resolve to the same node before retrieval improves. NLP.addPulp EntityLinker creates spaCy's EntityLinker, and linker.setAnnotations writes KBIDs onto the entity spans as ent.kbid. This compact tutorial uses known IDs so the data flow is visible. A trained linker would predict those IDs from candidates and context. The output shows mention text paired with graph-ready entity identifiers, which is the bridge from NLP to Neo4j. Now that we can link mentions, we need to put evidence into the graph as connected nodes instead of scattered text. This code stores evidence as connected graph structure instead of isolated text blobs. Vector search may return a nearby chunk, but it often has no native way to follow GraphRag to Neo4j and then to Cypher. The rows tuples keep the toy corpus readable, while driver.execute query sends a Cypher unwind query that creates entity nodes, chunk nodes, and the relationships between them. Merge keeps repeated runs from duplicating the same logical items. The output counts the distinct chunks now available for graph expansion, which gives retrieval something connected to traverse. With chunks in the graph and entities linked, the key graph RAG move is to expand from the linked entity to nearby chunks. This snippet retrieves evidence by walking relationships from the linked entity instead of only matching text similarity. Starting from seed ID, the Neo4j query follows paths up to 2 relationships away and returns distinct chunk text. That is the key graph RAG move. Connected evidence can surface even when the final chunk does not contain the exact query wording. The depth is an important trade-off. Increasing it can find more indirect context, but it may add noise and latency. Reducing it keeps retrieval tighter. The output shows graph expansion reached multiple chunks, including a connected Cypher detail. Finally, we need to pick the best small context to feed into a generator rather than sending every connected chunk. This code closes the loop from question text to a small RAG-ready context choice. Linker.setAnnotations gives the query a stable graph RAG ID, and driver.executeQuery uses that ID to retrieve connected chunks from Neo4j. The ranked line then prefers chunks that mention the target concepts in the question, so the final context is not just nearby in the graph, but also useful for the answer. The Boolean sort is a compact teaching reranker. In production, this slot is where a learned reranker commonly goes. The output shows the selected context chunk, which is the baseline result to pass into generation. You can map this toy flow into a real system by replacing the small toy corpus with your document store, and by logging which graph hops produced useful evidence. In a support knowledge base, for example, seed IDs would be product SKUs, and chunks would be troubleshooting steps linked to components and error codes. Quick recap. In 3 tight points, linking mentions to stable graph nodes lets retrieval expand along relationships and pull in indirect evidence. Use this when questions need multi-hop facts or when you already have curated facts in a graph. Be careful. Linker mistakes and overexpansion depth are the usual failure modes and can add noise. A practical next step is to tune the graph expansion depth parameter from 2 to 3 and measure answer precision on a small held-out QA set. That single change often increases recall for multi-step queries while revealing where a learned reranker is needed. If short, practical IR helps, subscribe and watch the IR videos.